Counting. The fundamental counting rule and permutations. How many 9-player batting orders are possible for a baseball team with 15 players? In order to answer this question, we first must become familiar with the fundamental counting rule. The fundamental counting rule states that the number of ways that a sequence of events can be performed is equal to the product of the number of ways that each event can be performed. Suppose a uniformed employee has for work shirts, 3 pairs of work pants, and 2 pairs of work shoes. How many different ways can this employee dress for work? The process of dressing for work for this employee amounts to performing a sequence of 3 events. The employee must first put on a shirt, then put on a pair of pants, and then put on a pair of shoes. There are 4 shirts to choose from, and 3 pairs of pants to choose from, and 2 pairs of shoes. The fundamental counting rule says that we should multiply these values together. So we will replace the word "and" with multiplication symbols. So there are 24 ways that this employee can dress for work. So now let's return to the question of how many 9-player batting orders are possible for a baseball team with 15 players. Designing a batting order is the same as a sequence of 9 events. The manager must select a player to bat first, a player to bat second, and so on until the entire batting order is filled. If there are 15 players on the team, then there are 15 ways to fill the first batting position. That would leave 14 players to choose from to bat second, 13 to bat third, and so on until all of the 9 batting positions in the order has been filled. Remember that the fundamental counting rule tells us to multiply the number of ways that each event can occur in order to find the number of ways that the sequence can be performed. So there are 1,816,214,400 different ways to make a 9-player batting order for a team with 15 players. The batting order problem can also be carried out using a permutation. A permutation is an arrangement of n objects in a specific order using r objects at a time. The notation is NPR, and the formula is n factorial divided by n minus r factorial, where n is the number of items available to choose from, and r is the number of items to be chosen and then arranged. Designing a batting order is basically an arrangement of 15 objects taken 9 at a time. We are to arrange 9 players from a group of 15. N will be the number of items to choose from, which is 15. And R, which is the items to be chosen then arranged, here will be 9. 15p9 is equal to 15 factorial divided by 15 minus 9 factorial, which would be equal to 15 factorial divided by 6 factorial. 15 factorial is defined as 15 times 14 times 13, and so on until you get down to 1. 6 factorial is defined as 6 times 5 times 4, and so on until we get down to 1. But the factors from 6 to 1, notice here, will cancel and leave us with the same list of factors that we found using the fundamental counting rule. And therefore, we have the same result of 1,816,214,400. Let's follow along with our notes. Fundamental counting rule. In a sequence of n events in which the first one has k sub 1 possibilities, and the second event has k sub 2, and the third has k sub 3, and so forth, the total number of possibilities of the sequence will be the product of the number of possibilities of each event. In particular, k sub 1 times k sub 2 times k sub 3, all the way up to k sub n. Notice that the word "and" means to multiply in this case. For example, a yarn shop has hat patterns in 4 styles, with 5 stitch options, 3 sizes, and 8 yarns that are appropriate for the hat. How many different hats can be made? Also, how many hats can be made if size is disregarded? Since we're going to start with regarding size, there are 4 times 5 times 3 times 8, giving us a total of 480 different types of hats that can be made. Again, 4 styles, 5 stitch options, 3 sizes, 8 different yarns. But if size is disregarded, we simply remove that factor from this product, giving us 4 times 5 times 8, equaling 160 different hats that can be made if size is disregarded. In the next example, the sample space for each event will be the same. However, in one case, repetition is allowed, while in the other case, repetition is not allowed. A lottery game called Pick 4 is played by picking 4 digits, 0 through 9. How many sets of 4 digits are possible if digits can be repeated? How many sets of 4 digits are possible if digits cannot be repeated? First, let's begin if digits can be repeated. If digits can be repeated, then there are 10 options for each of the 4 picks. Remember, we're talking about the digits from 0 to 9. There are 10 options there. Therefore, the number of total picks would be 10 times 10 times 10 times 10, equaling 10,000 different types of picks. However, if we are not allowed to repeat any options or repeat any digits, then the first pick has 10. The second will only have 9 options to choose from because the first has already been chosen. The third will only have 8. The fourth will only have 7. And of course, multiplying these together will give us 5,040 possibilities. Factorial formulas. For any counting number n factorial is defined as n times n minus 1 times n minus 2 times n minus 3 times n minus 4, all the way down to 1. Keep in mind that 0 factorial equals 1, a very important side note. So as an example, 5 factorial means simply 5 times 4 times 3 times 2 times 1. A permutation is an arrangement of n objects in a specific order, that is, order matters. So because it's an arrangement, order, again, matters. A very important phrase when it comes to permutations. First, consider the instance where all n objects are different. When all objects are used, then the permutation of n objects, n at a time, is written as follows. This is the notation. And calculated using the following formula. N factorial. However, we don't typically do that. Typically, only R of the n objects are used in a specific order. Therefore, the permutation of n objects, R at a time, is as follows. NPR equals to n factorial divided by n minus r quantity factorial. Let's look at an example. Suppose a home nurse has 6 patients that must be visited in one day. How many different ways can the nurse visit them? B. If the nurse must choose 4 to visit in one day, how many ways can they be chosen? Let's start with part A. If all 6 patients must be visited, there are 6 patients that can be visited first. So 5 that can be visited second, then 4 that can be visited third, and so forth. So the number of ways that you can visit 6 patients in one day is 6 factorial. 6 times 5 times 4 times 3 times 2 times 1, giving us 720 different ways we can visit 6 patients in one day. To continue part A, let's also take a look at a permutation. Let's go ahead and note that the formula works here because 0 factorial is defined to be equal to 1. So 6p6 will still equal to 720. B. If the nurse must choose 4 to visit in one day, how many ways can they be chosen? 4 of the 6 patients must be visited. There are 6 patients that can be visited first, so 5 that can be visited second, and 4 that can be visited third, then 3 that can be visited fourth. So that would be 6 times 5 times 4 times 3. Or, using the formula, that is to say 6p4 is equal to 6 factorial divided by the quantity 6 minus 4 factorial. Either way, we get the same answers because you'll notice that the 2 and the 1 cancels each other out, giving me the same product as above. Now at this point you may be thinking, why use the permutation rule when it's just as easy to just simply use the fundamental counting rule? You'll see later that the permutation rule is actually quite useful. More on that later. Permutation rule number 2. Now let's go ahead and consider when objects are identical. In the last example, the objects were not identical. Clearly, 6 patients are 6 individuals, so that would be a different situation. But what if the objects were identical? How would that change the permutation rule? Permutation rule number 2 states that the arrangement of n objects in a specific order using r sub 1 objects that are identical, r sub 2 objects that are identical, all the way up to r sub p objects that are identical, will follow this formula here. N factorial divided by r sub 1 factorial times r sub 2 factorial all the way up to r sub p factorial, where r sub 1 plus r sub 2 plus all the way up to r sub p is equal to n. So let's do an example. How many permutations of the letters can be made from the word Mississippi? So here you'll notice that there are 11 letters with one unique M. However, there are 4 I's, 4 S's, and 2 P's. Because some of the objects are identical, we need to consider the second permutation rule. Therefore, the number of permutations that can be made up are as follows. Since there are 11 letters in the word Mississippi, we start off with 11 factorial in the top, and in the bottom we divide by the fact that we have 1 letter for M, 4 letters for I, 4 letters for S, and 2 letters for P. Giving us a grand total of 34,650. Now let's look at combinations. A combination has similarities to permutations. However, a combination is a selection of distinct objects without regard to order. Recall that a permutation required that the order be taken into account. A combination does not take order into account. A very important distinction. Combinations are used when the order or arrangement is not important, just like in a selecting process. Suppose a committee of 5 members is to be selected from the organization membership of 45. 5 selected committee members represent a combination. So imagine if you have an organization with 45 people and you just simply needed 5 people to go to a conference to represent the organization. If it doesn't matter which of the 5 go to the conference, then that is a combination. The number of combinations of R objects selected from N objects is denoted by NCR and is given by the following formula. It starts off just like a permutation. N factorial in the top, and even in the bottom is N minus R factorial, but with one added factor in the bottom. That is to say, another factor of R factorial. Example, how many different tables of 4 can you make from 12 potential bridge players? The question asks for how many different groups of 4 players can be selected from 12 potential bridge players. This is a combination because they don't name people, they don't say they're specific individuals. Each person is treated as an identical object. Therefore, in this case, N is 12, and we're choosing 4 people. So the combination is as follows. 12 factorial in the top, and the bottom is 12 minus 4 quantity factorial, which becomes 8, times 4 factorial. Simplifying this, continuing on, we end up with 495 different combinations. If a person can pick 3 presents from 12 presents under a Christmas tree, how many different groups of presents can be chosen? This is still a combination. This is assuming that a person does not know what is inside the presents. Now clearly, you have presents that are more valuable than others. But here, since it's not specified, they are all treated as identical objects. Simply put, out of the 12 presents, we choose 3 of them, giving us 12 factorial divided by 12 minus 3 is 9 factorial times 3 factorial. You should end up with 220 different combinations.